Water available from precipitation or rainfall that is captured must be stored or retained within the soil. That is the basic principles of water retention. Water retention can be ensured by three practices: by reducing evaporation, by controlling weeds, and by deep percolation, so as to maximize the water retained in the soil for utilization by the growing crops. Evaporation is the loss of water from soil surface mainly, or from the external environment of crop. Evaporation can happen even before the soil water is stored in the soil. It can happen before the crop planting or during the crop growing season. Evaporative losses before crop planting reduce the amount of water available for the succeeding crop. Fallowing is a useful practice to increase the amount of water stored in the soil, but the storage efficiency depends on soil physical properties, rainfall patterns, and the evaporative demands. For example, in arid and semi-arid areas, the storage efficiency may be as low as 0% in sandy soils. In climates with relatively low evaporative demand and winter rainfall patterns, the storage efficiency may be as high as 85%. Evaporation occurs in two or three stages. The first stage depends on the net effect of environmental conditions and water flow to the surface. Environmental conditions which affect evaporation during the first stage are wind speed, temperature, relative humidity, and radiant energy. During the second stage, losses decrease rapidly as the soil water decreases, and in second stage the rate of evaporation depends mainly on soil conditions that control water flow to the surface. During the third stage, when water moves to the surface as vapor, the rate of evaporation is low and it is controlled by mainly by adsorptive forces at the solid liquid interface. If we have to decrease the rate of evaporation, the greater potential lies in the first two stages. According to Hillel, the evaporative flux can be modified in three ways. Number one, by controlling the energy supply at the site of evaporation. For example, by modifying soil albedo through color changes. Number two, by reducing the potential gradient driving water upward through the soil profile. For example, by warming the surface layer so as to set up a downward acting thermal gradient which restricts upward movement of water. And number three, by decreasing the conductivity of the profile, particularly of the surface zone, for example, by tilling the soil. So during the first stage of evaporation, the meteorological conditions dominate the rate of evaporation, whereas during the second stage, the soil hydraulic properties dominate the rate of evaporation. Soil evaporation is a complex process that depends on the gradients of soil water potential, soil temperature, as well as the atmospheric conditions. For example, when the soil is wet and the air is dry, the rate of evaporation will be high. And soil water potential continues to change with the addition of water by precipitation due to use by crop plants or due to the increase in the rate of evaporation. Changes in soil temperature affect the vapor pressure of water according to the Charles Boyle's law that increases with temperature. The atmospheric conditions such as solar radiation, wind speed, and humidity also affect the rate of evaporation. For example, solar radiation provides the energy uh, required for evaporation. Similarly, high humidity and low wind speed result in a low vapor pressure gradient at the soil atmosphere interface, and hence there is a low evaporative demand. So there are many practices which can be used to manipulate the rate of evaporation from soil by by providing a barrier to prevent the water vapor movement from soil, to negate the energy available for evaporation, or to minimize or disrupt water flow within the soil. So most of these effects are achieved by mulching or by tillage or tilling the soil. According to the Soil Science Society of America, any materials such as straw, sawdust, leaves, plastic film, loose soil that is spread or formed on the surface of the soil to protect the soil and plant roots from the effects of raindrops, soil crusting, freezing, and evaporation is called as mulch. Crop residue characteristics that affect the rate of orientation are orientation, which affects the thickness and porosity of the layer, uniformity of the layer, reflectivity, and the aerodynamic roughness resulting from the residues. The reflectivity affects the radiant energy balance at the surface. The value of crop residues for water conservation depends on several factors such as the quantity, type, and placement of residues, evaporation potential, length of fallow period, precipitation, tillage, and type of soil, as well as wind speed. Crop residues are most effective during the rainy season because they reduce the amount of energy that arrives at the wet soil surface. The conservation tillage approaches advocate maintaining crop residues on the soil surface. Compared to the conventional system in which 15% or less, often 0% crop residues are left on the soil surface, conservation tillage aims at maintaining 30% or more crop residues on the soil surface. The, the economic value of crop residues for animal feed or as fuel or for industrial uses, the practice of leaving crop residues on the soil surface is rarely seen. Other than crop residues, the the type of mulch that is highly recommended and has proved its utility are plastic films. Particularly in China, the plastic sheets of as much as 0.005 to 0.007 millimeter thickness uh, are used, for example, in corn-based system, and special equipment is available for spreading those rolling type plastic films in the field for planting as well as for application of fertilizers. Those plastic films or plastic mulches have two main advantages. They can capture almost every drop of water, and they retain maximum amount of water in the soil by reducing evaporation. Another advantage of plastic mulches is that they can raise the soil temperature, thus reducing the growth duration as well as opening a window for sowing even before time. Conservation tillage is still a non-conventional approach. However, uh, a conventional approach is tillage at a shallower soil depth that reduces the capillary water flow to the soil surface. This is called as dust mulching or soil mulching and has been proven to be effective to reduce or curtail the rate of evaporation under particular situation. For example, when there is a distinct rainy season followed by a distinct dry season, such as monsoon rainy season followed by a dry winter season. Weeds are the undesirable plants that compete with the normal crop plants for light, space, nutrients, and water. Therefore, it is important to manage weeds or to keep them below the critical threshold level for conserving soil moisture. However, in some situations, for example, during a fallow period, sometimes it becomes important to keep the soil covered with weeds to control erosion and enhance the infiltration. But in this case, a balance must be maintained uh, in favor of the amount of water stored or in favor of the increased rate of infiltration. This can be achieved, for example, by the control into the soil is called infiltration, while its downward movement through the soil is called percolation. So the water moves out of the root zone, uh, making it unavailable for crop use, and sometimes also moving the nutrients beyond the rooting depth and causing the groundwater pollution. To reduce the amount of water lost by percolation, there are certain management practices which can be applied to, to manage the deep percolation. To reduce the potential for percolation losses, crops sowing time should be adjusted such that it matches the season when the potential for percolation is the greatest. Management methods or practices that encourage deeper plant rooting or deep tillage, planting deep rooting crops, or cultivars that extract water from deeper layers in the soil profile, and adequate fertilization for proper root propagation. Some other practices to control deep percolation include bringing materials to the surface that retain more water by deeply plowing the soil, installing subsurface barriers such as asphalt barriers at 60 centimeter depth, and by adding organic matter to increase the water holding capacity of soil. Regarding deep plowing, it is a costly operation and must be carefully considered before implementing. Although adding organic materials to soil has proven its benefits for improving water retention, improving soil structure, and root proliferation, and thereby reducing deep percolation, such improvements under dryland conditions are difficult to achieve. This is because under dryland conditions, due to sparse canopies, the amount of crop residues are too low. However, any improvements in soil structural conditions will be beneficial in regards to water infiltration, retention, and use by crops even under dryland conditions.